NASA unveiled pictures from a new space telescope capturing the deepest images of the universe anyone has ever seen.
When the James Webb Space Telescope JWS turned its infrared gaze deep into the cosmos, scientists anticipated new insights into the early universe, exotic exoplanets, and ancient galaxies. But what it recently revealed sent shockwaves through the astrophysical community. In a region of space previously thought to be quiet, distant, and thoroughly understood, JWST encountered a celestial phenomenon so unexpected that it defied nearly every existing cosmological model. Nestled among ancient galaxies and primordial light, the telescope captured high-resolution data on a formation that, by all known laws of physics, should not exist. Before we start, smash the like and subscribe buttons for more updates. The JWST detected a cluster of ultra-massive galaxies, compact, luminous, and intensely active, not just older than expected, but appearing to have formed a mere 300 to 400 million years after the Big Bang. These galaxies weren't the diffuse, slowly assembling clouds of gas that current models predict for such an early epoch. Instead, they exhibited mature structures, dense stellar bulges, organized rotational motion, and supermassive black holes at their cores. One of them in particular displayed a degree of mass concentration and stellar activity that rivaled entire modern galactic systems. Its light had traveled across more than 13 billion years of cosmic history, yet its structure and behavior looked disturbingly contemporary. The implications were nothing short of paradigm shifting. For decades, astrophysicists have worked within a framework where structure in the universe forms hierarchically. Small clouds of gas collapse under gravity, gradually accreting mass and merging into larger entities. The early universe under this model should have been dominated by protogalactic fragments, chaotic, irregular, and inefficient at star formation. But what JWST observed was the opposite: a clean, mature galactic system already teeming with stars and governed by internal order. The mere presence of such a system so soon after the universe's birth challenges fundamental assumptions about how matter clumps and evolves. This impossible encounter didn't stop with just one anomaly. The telescope's instruments continued to pick up similar candidates in its deep field surveys, other galaxies with stellar masses exceeding what should have been achievable at that point in time. Some even suggested the presence of population 3 stars, hypothetical first-generation stars composed purely of hydrogen and helium, but arranged in structured spirals and spheres rather than amorphous clusters. The sheer mass density of these objects implied rapid star formation rates and astonishing efficiencies that defied any simulation run to date. What made these observations more profound was their clarity. The JWST's infrared capabilities allowed it to pierce through cosmic dust and gaze back to the universe's formative moments with unprecedented resolution. Unlike previous missions that hinted at anomalies through faint glows and redshifts, JWST delivered crisp imagery and spectra that laid bare the physical processes at work. Emission lines indicated the presence of ionized elements heavier than helium, signs that nuclear fusion and supernovae had already enriched these early galaxies. Somehow, chemical evolution had unfolded at breakneck speeds, leading to the formation of metals, magnetic fields, and complex dynamics in mere cosmic instants. Equally perplexing was the detection of gravitational lensing effects caused by these early galaxies. In several cases, the JWST documented background light being warped around these structures, suggesting that their mass, not just visible matter but also dark matter, was substantial. This contradicted the standard cosmological timeline, where significant dark matter halos shouldn't have coalesced into such dense nodes so early. Either the nature of dark matter behaves differently under extreme early universe conditions, or our understanding of its role in structure formation is critically flawed. The tension grew further when computational models failed to replicate the observations. Simulations designed to mimic the early universe couldn't reproduce galaxies of such mass and maturity without tweaking fundamental constants or invoking exotic physics. Some theorists proposed variations of inflationary scenarios, suggesting that localized density fluctuations could have led to the rapid formation of galactic cores. Others considered whether the laws of gravity behave differently at small scales under high energy densities, potentially invoking modified gravity oddity theories or early universe phase transitions. More radical voices entertained the idea that the cosmos is cyclic, or that there might be an unknown pre-Big Bang history influencing current observations. Perhaps the JWST was catching echoes or remnants of a previous cosmic iteration, survivor structures that somehow carried forward through a rebirth of space and time. Though speculative, these ideas gained a foothold amid the overwhelming mismatch between expectation and reality. The discovery also reignited debates over the accuracy of cosmic chronometers. If the redshifts observed in these galaxies are misinterpreted due to unknown intervening effects, the entire timeline of the early universe might need recalibration. However, JWST's spectroscopic precision, confirmed across multiple filters and instruments, made such errors unlikely. It seemed more probable that the standard model of cosmology, currently anchored by the lambda cold dark matter framework, needed a major revision. While the scientific implications reverberated through academic institutions, the broader cultural impact was just as significant. For the first time in generations, cosmology was once again facing foundational uncertainty. The early 20th century had witnessed Einstein's revolution, and the late 20th century had grappled with the accelerating expansion of the universe. Now, in the early 21st century, the JWST was ushering in a new era of cosmic disorientation. The universe, it turned out, was not simply older and deeper than expected, it was also more mature, structured, and strange at its very inception. This encounter also prompted renewed questions about the nature of time and causality. How could such complex systems arise without a long buildup? Were there hidden variables or fields influencing early structure formation? Could there be unknown particles or forces operating at scales and energies unreachable by current particle physics? These questions didn't just concern astrophysics, they bled into quantum theory, philosophy, and even metaphysics. What did it mean for a galaxy to exist so early? Did it require rethinking how we define emergence and evolution on cosmological scales? Scientists began re-evaluating their data from past missions like Hubble and Spitzer, wondering whether earlier hints of these mature systems had been missed or misclassified due to limited resolution. In many cases, the clues had indeed been there, buried in the noise, too ambiguous to draw firm conclusions. JWST's unprecedented clarity didn't just reveal new things, it recontextualized old data, giving it new weight and meaning. Another consequence of this impossible encounter was a reinvigorated focus on high redshift astrophysics. Ground-based observatories and radio telescopes aligned their priorities to target the same regions, seeking corroborating evidence. The Atacama Large Millimeter Submillimeter Array ALMA identified unexpected molecular lines in the same vicinity, suggesting that these galaxies hosted significant reservoirs of cold gas, a requirement for sustained star formation, but also an enigma considering the universe's infancy. There was also the question of how these galaxies managed to avoid the feedback mechanisms that typically slow or prevent early star formation. In standard models, rapid starbursts tend to blow away gas through winds and radiation, quenching further formation. Yet these newly discovered systems appeared to sustain high-efficiency star production over extended periods without such regulation. It was as though the universe had a shortcut, a cheat code for complexity, that allowed certain pockets to leap ahead in the cosmic race. In the months following the discovery, theorists and observers collaborated more closely than ever. Proposed missions were quickly reshaped to follow up on JWST's findings. Several scientists suggested deploying space-based interferometry to capture even finer details of these early structures. Others advocated for deeper field surveys to determine whether these impossibly early galaxies were rare outliers or common constituents of a hidden cosmic architecture. If the latter were true, it would suggest that our models were not just slightly off, they were fundamentally misaligned with reality. The JWST had not just taken a picture of the past, it had exposed a gaping hole in the story we tell about the universe's birth and growth. The notion of a smooth, gradual emergence from simplicity to complexity now faced real scrutiny. The cosmic timeline, once thought to be a gentle unfolding, looked increasingly like a turbulent, chaotic burst of activity, a fireworks display of matter and light occurring in the darkness of the universe's earliest moments. This impossible encounter underscored the profound role that observation plays in shaping theoretical landscapes. For all the elegance of mathematical models and the predictive power of simulations, it is the stubborn, unyielding nature of empirical data that forces science to evolve. The JWST, with its golden mirror and silent vigil among the stars, had done more than look back in time. It had punctured the veil of certainty, revealing a universe far stranger, more efficient, and more precocious than previously imagined. The enormity of this discovery discovery will ripple through cosmology for years to come. Every model of dark matter, every equation of state, every assumption about galactic evolution will have to reckon with these impossible structures. In a way, the James Webb Space Telescope has acted like a cosmic archaeologist, unearthing artifacts from a time no one thought could produce them. It's as if a child stumbled upon an ancient cathedral in a forest where only tents were expected to exist. And this was just the beginning. The telescope's deep scans hinted at more anomalies, more impossible objects lurking just beyond the edge of its current surveys. The cosmic frontier had expanded, and with it, our understanding of what the universe is capable of. The laws of physics had not changed, but our grasp of them had been undeniably shaken. The cosmos, as seen through the eyes of JWS, was not just older and vaster, it was more mysterious, more dynamic, and infinitely more surprising than anyone had dared to believe. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on James Webb's impossible deep space encounter? We want to hear from you. Thank you for watching, and see you next time.